Assalamualaikum warahmatullahi ta'ala wabarakatuh. Welcome to another video on MCTE 2311 Signal and System Analysis. In this video, I will start on a new topic, which is Fourier transform. So for introduction, if you still remember in our previous lecture where we study Laplace transform, we say that we use the Laplace transform to analyze our system and signal in the frequency domain or the S domain, where we are given that S equals to sigma plus j omega. But this form is valuable for system analysis. However, it is not quite suitable for signal analysis because in the signal analysis, we prefer to represent the signal in terms of e j omega instead of e to the power of st. Okay, so for signal analysis, we prefer to use the Fourier transform, where the Fourier transform is a special case of the Laplace transform, because in the case of the Fourier transform, S is equals to j omega only. The Fourier transform can be used to analyze a periodic signal, which is this signal that does not repeat itself after a certain period, which is different from the Fourier series that can only be used to analyze periodic signal. However, one thing that you want to take note is that not all signals are Fourier transformable. So if you read the textbook, the BP Lati textbook, there are some explanation on the type of signal that are not Fourier transformable. So to understand this, I want you to look at this equation, which is the Laplace transform equation, and we have seen a few sample problem on how to use this equation to do the Laplace transform of a given signal. And this is the equation for the Fourier transform. So instead of x of s, we have x of omega. And here the s here is replaced with j omega. And the same we have to do integration over a certain limit. Now to practice on using this equation, here I give one sample problem where you are asked to determine or to find the Fourier transform of x of t equals to rectangle t over tau, shown in the figure below. So this is the signal, which is also known as the gate pulse signal. So this is x of t. Alright, so in order to solve this problem, to determine the Fourier transform of this rect t over tau, first let's have a look at this graph. And let's find the mathematical definition of this graph. So x of t, if you look at this graph, we know that x of t is equals to 1 when t is in between minus tau over 2 and tau over 2. So x of t is 1 at this region, between this and this time frame, and it is 0 elsewhere. So smaller than minus tau over 2 and greater than tau over 2, x of t is 0. Now that we have the mathematical definition of this signal, let's use the Fourier transform equation to determine the Fourier transform of this equation. So we are given x of omega equals to the integration from minus infinity to infinity for x of t e minus j omega t dt. So in our case, x omega equals to, if we integrate from minus tau over 2 until tau over 2, so minus tau over 2 until tau over 2, x of t is 1, okay, which is from this definition. So you have 1 e minus j omega t dt. So if I integrate this, 1 is just a constant, so I will get minus 1 over j omega e minus j omega t. The limit is minus tau over 2 to tau over 2. Okay. So next is replace this t with tau over 2 and minus tau over 2. So I will have x omega equals to minus 1 over j omega. It will be e minus j omega tau over 2. Okay, so we replace this t with tau over 2. So I will have tau over 2 minus e. So here I have minus, and here I also have minus. So I will have positive j omega tau over 2. Okay, so now when we arrive here, let's modify this a little bit, okay, so that we will have a form that is familiar to us. So let's multiply this negative inside, and at the same time we bring this j also inside. So we will have 1 over omega. So we will have, you multiply the negative, this part will be positive. So e j omega tau over 2, this one will be negative, minus e minus j omega tau over 2, and I bring the j also inside, so I will have over j. Okay, sorry, j. So now this form, okay, this form is familiar to us. Okay, if you still remember when we study the Fourier series, okay, I already told you that if we have sine omega t, then it is equivalent to the exponential complex signal of e j omega t minus e minus j omega t over 2j. Okay, so this form is actually similar to this, except for the 2 here, right? So it means instead of sine omega t, we will have, for this part, we will have 2 sine omega t. Okay, and the one in the bracket, instead of just omega t, it will be omega tau over 2. Okay, so this one we can actually replace with 2 sine. Okay, so instead of omega t, we will have omega tau over 2 divided by this omega. Okay, omega. Okay, now I want to modify this again so that I will have another familiar form of signals. Okay, so what I will do is I will multiply the numerator and the denominator with tau over 2. Okay, because I want this omega to be similar to this one. Okay, and I multiply this with tau over 2 as well. Okay, so I will have x omega equals to this, for the numerator, this cancel out. So I'm left with tau and sine. So tau sine omega tau over 2 over omega tau over 2. Now this form here, okay, this is similar to this signal. Sinc of x equals to sine x over x. Okay, so this part we can replace with tau sinc of omega tau over 2. Okay, so this is the answer. Okay, so this is the Fourier transform of this x of t, which is x of omega. Okay, so this is the sinc function. Okay, so this is the general form of sinc of x, which is sine x over x. So if we look at this signal, we can see that it is the amplitude of this signal is 1, okay, at x equals to 0. So this is x at x equals to 0. When x is pi, okay, the signal is 0. At x equals to 2 pi or at minus 2 pi, the signal is 0. Okay, which means for sinc of x, it is equals to 0 when x is equals to plus minus n pi, where this n is integer 1, 2, 3 and so on. Okay, which what you can see here, pi, 2 pi, 3 pi, your signal is 0, the amplitude is 0. Okay, so in our case, what we have is sinc omega tau over 2, right? This is what we have. So our signal will be equals to 0 when, okay, when omega tau over 2 equals to plus minus n pi. Okay, so here if we can say that omega equals to plus minus n 2 n pi over tau. Okay, so instead of at pi, okay, our signal will be 0. Okay, so you will have an amplitude, okay, of let's say 1 or a certain value of amplitude there, and then here it will be 0 at where this n is integer 1, 2, 3 and so on. So it will be 0 at 2 pi over tau, okay, and then it will be 0 again here at 4 pi over tau. Okay, so you substitute this n with 1, substitute this n with 2. Okay, so that is the value where the sinc omega tau over 2 will become 0. Okay, so if I plot the graph, it will look like this. Okay, so we have the rect t over tau, okay, the Fourier transform. This is the symbol for the Fourier transform. If you still remember, the symbol for the Laplace transform is L, like that. Okay, so this is the symbol for the Fourier transform. So it is equivalent to tau sinc omega tau over over 2. Okay, and in the graphical form, okay, this is the pulse gate in time domain, and this is the Fourier transform, okay, which is in omega. Okay, so you have here x of t and this is x of omega. Okay, so this is the end of this video. I will see you in the next one for another sample problem. Okay, thank you.